So thank you everyone again. Interest and participation and attendance and everything. The first thing that I'll say is just that there will be a photo taken for the event tomorrow morning, prior to or during the coffee break in the morning. So at 10:30 or 11:30 or something. So brush your hair. And so.
All right, our first speaker this morning is John Loftin from Rutgers, who is talk about cubic differentials and harmonic maps into an asymptotic cone.
Okay, thank you. I'd like to thank the organizers for the invitation. It's great to be back at IMPA and back in Rio. It's a very nice setting for doing some mathematics. So this is going to be joint work with Andrea Tamborelli and Mike Wolf. So cubic differentials and harmonic maps into an asymptotic cone. Okay, so the main thing that, just to kind of set this up, so I'm going to let sigma be kind of a closed Riemann surface. With the genus at least 2, so of hyperbolic type, and let U be a cubic differential. On sigma. And so in other words, what that means is that kind of locally, U is some f of z times dz cubed. So f of z is just z is a local holomorphic coordinate. F of z is a holomorphic function, and then dz cubed. Another way of saying this is kind of, if you want to use kind of a more algebraic geometry notation, so U is a holomorphic section of the, so this is going to be the canonical bundle, which is generated by dz. So k cubed, that's going to be dz cubed, cubic differentials. Good? All right. And so what we're interested in studying, I mean, it seems like kind of a special case, but I'll show you, I hope that we can, so what we want to do is we want to consider some structures, which I'll talk about in a bit. So corresponding to, so the Riemann surface is going to be fixed. We're going to scale U by a positive real constant, so as t goes to plus infinity. Okay? And so what we're going to do is, I'll show you just kind of a little bit of how this is going to work. So, so the t equals 0 case, this is going to be a hyperbolic metric. On sigma, but when we do kind of take the appropriate limit, as t goes to plus infinity, we'll see another metric. So if U is a cubic differential and you take its absolute value to the 2/3 power, then this is of the kind of a tensor of the type of a metric, a conformal metric on the Riemann surface. And so this properties of this metric are, this is okay. So it's going to be have non-positive curvature. Another thing is that it's going to be flat away from the zeros of U. And so this is actually not so difficult to see. So basically what you can do away from the zeros of u, you can always find a local conformal coordinate such that u is exactly equal to dz cubed. And so that's just, if you do this formulation, that's the standard flat metric. Okay? And then you're going to have, so near a 0 of order m, so in other words, u is approximately z to the m dz cubed, then we're going to have kind of a cone angle of more than 2 pi, so 2 pi plus 2 pi m over 3 at the 0. Okay? So this is kind of the standard, so this cone angle has to be more than 2 pi in order to have non-positive curvature. So you can think about this as a conformal metric on the Riemann surface, which is flat almost everywhere, but has kind of a negative delta functions of curvature at all the zeros. Okay. So let's talk about some more properties. So I guess in terms of geodesics, so that you can still talk about geodesics here, which are just locally length minimizing paths. So these are going to be straight lines in these in the flat coordinates away from the zeros. And then there is, but kind of passing through a 0, so what happens is, so if you have kind of a straight line coming into a 0, then there are multiple possible ways for this to continue. And so what you want to ensure is you need this kind of Euclidean angle to be at least pi on both sides. So this is going to be at least pi, and this is going to be at least pi. Okay? So that's the property of length minimizing. So I guess another feature is that so between any 2 points, so let's kind of go to the universal cover here. On the universal cover, there is a unique geodesic between them. Okay? And typically this will kind of, it will be flat line segments, and then it will hit some number of zeros and kind of have some sort of, it's going to look like it's going to bounce off a little bit through the zeros. And then another important feature is that, so there's going to be this non-unique continuation of geodesics when you pass through a 0. Okay. So in particular, there's so this total angle when you're passing through the 0 is going to be strictly greater than 2 pi, and so there are many kind of if your geodesic is coming in this way, then in order to continue, there's going to be many possible directions after that.
So the universal cover here is just the classical universal cover of the smooth.
Yeah, just the yeah.
You're not making any compensation for the singularities.
No, I'm not making any compensation for the singularity. So just sigma itself. Yeah. Okay. Okay. So I'd like to kind of just to say a little bit about how we might do this and talk about the geometry. And so I think for this talk, I'm going to talk about this as kind of a case of Higgs bundles. So this is going to be an important special case of Higgs bundles. There are many other ways to talk about this, but just this is going to get me kind of to where I need to go the fastest. And so this is, these were of course introduced by Hitchin, and then kind of the basic theory of that we're using is kind of also due to Simpson and Donaldson and Corlett. Okay, so let curly E be a holomorphic vector bundle over sigma. And so we're going to make a restriction that just kind of makes things a little bit nicer. So I'm going to have the determinant line bundle of E be 1, which is my notation for the trivial holomorphic line bundle. The trivial line bundle. Okay, so capital phi is going to be a Higgs field. And so this is going to be a section, a holomorphic section of endomorphisms of the bundle tensor the canonical bundle. And so this should be kind of very suggestive because if you write this, if you were to write this in terms of indices, then this is exactly the sort of thing that you would use to the indices. There's going to be one up and one down in terms of E, and then there's going to be this dz. It's like a cotangent vector on the Riemann surface. These are the indices that you have for Christoffel symbols. So this is going to be part of a connection. Okay. So then if there's kind of a, so I'm not going to talk that much about this. If this pair, E of E and capital phi, is stable, which is kind of a generic condition, then we have, so M, this is going to be a harmonic metric on E, and I'll explain what that is in a minute. And we're going to create a connection on E. So nabla, so this is going to be the Chern connection. So M is going to be our Hermitian metric on E. It naturally has a Chern connection. And then we're going to add in kind of the Higgs field term. That's going to be part of this connection, and then also the adjoint with respect to the metric. Yeah, good. And so then the condition here is that nabla is flat. Okay? And so one can kind of write this down. So this is going to this would be kind of the Hitchin system of equations in terms of kind of the metric n. Okay? All right. So then, since nabla is flat, I mean, I get to kind of say the word holonomy here, but kind of the local holonomy of a flat connection, of course, is trivial. So if you kind of take a small loop around a base point, kind of based at a point, then you just come back to the same thing under parallel transport. But what you get instead is you get some non-trivial holonomy if you go around kind of non-trivial loops that might be in pi 1. Okay? So you get kind of a holonomy map. So from so in this case, it's going to be SLNC. So N is the rank of E. Okay? So you get this flat connection.
That's called monodromy.
Monodromy, yeah. Yeah. Yes, monodromy, holonomy. So these words are, I'm not sure exactly when I'm supposed to use with each one, but I mean, they're kind of different. All right. Okay. So, and then also this, this M is a harmonic metric. And so M you can think of is, this is a map from the universal cover into kind of the space of Hermitian metrics. And so the space of Hermitian metrics is just the symmetric space of non-compact type that you get from this Lie group. So you take kind of a maximal compact, which would be SUN, and so this is going to be, and so this is harmonic and is equivariant with respect to the holonomy, okay, or monodromy. Good? So this is kind of you get kind of a lot of structure from this thing. And so I'm going to kind of quickly kind of go to a special case here. So a special case for us. So this is, so I'm going to do a,
So the point is on the universal cover, so the bundle is actually
yeah. So on the universal cover, everything is trivial. So, but I mean, it's just useful. So in this, sometimes you call this like a twisted harmonic map. That's just, it means it's a section of a bundle, right? And so then the transition functions of the bundle are determined by this holonomy. Okay, so we're going to look at this special case, and this special case is, was introduced by Hitchin. And we're going to look at a very special kind of sort of Higgs field here, which also follows Hitchin's okay. So U is kind of a cubic differential. And then 1, it turns out, so since this bundle is made out of kind of the trivial bundle and the canonical bundle, if you kind of work through what phi has to be here in these various slots in the matrix, this is just an endomorphism of the trivial bundle. And then U is naturally a cubic differential. So you can kind of, I'll leave you to work that out. So this is going to be the Higgs field. And then in this case, we're going to have kind of the metric has a very special form. So it turns out that the metric that you get from this construction is diagonal, where kind of H is kind of a conformal metric on sigma, okay? So in kind of other situations, you may call this kind of a Blaschke metric, or this is kind of related to something called a Toda system for A22. And so also in this case, there's an extra symmetry. So the holonomy of nabla is conjugate to, lives in SL3R. And so for this, Hitchin kind of introduced a real structure on these bundles, which is not just kind of you take the matrix and go to the bar. It's not the standard one, but it's not that difficult. So this is conjugate under kind of a certain real structure. So this is inside of SL3C. So, and then of course, kind of the parallel transport will give you, of nabla will give you the holonomy.
Sorry, are you talking about, is this the nabla M, or which connection? There's several connections floating around right now.
This is nabla, okay.
That's the flat one.
That's the flat one. Yeah, nabla is the flat one. Nabla M is the Chern connection.
So the holonomy is contained in SL3R.
Yeah, so it's, that's right. It's conjugate to being contained in SL3R. Yeah. Good? All right. Next. So the thing is, this looks like a very special case, but it turns out that this stuff is that these data, so if you take kind of a Riemann surface and a cubic differential, these these parameterize a component of the representation variety of representations of pi1 of sigma into PSL3R. Okay? And so this is called the Hitchin component. And so I guess when Hitchin first introduced Higgs bundles, I mean, his first application was to kind of give a new parameterization of Teichmüller space, which is kind of the space of all conformal structures. So in this situation, you can parameterize all of these representations. And so these are naturally kind of a generalization of Teichmüller space. And so this kind of uses kind of a lot of, there's a lot of background here. So there's some kind of old work of myself, of Labrie, of Hitchin, of course, of Choi and Goldman. And if you kind of, Cheng and Yao, kind of in terms of affine differential geometry. So this, yeah. So Hitchin's original case was PSL2R, and so this is the PSL3R case. Yeah. Okay? Yeah. So the thing is that you can use this. You can do something similar for quartic differentials, and then that will give you representations into SP4R. And there's a similar thing for sextic differentials, although the matrix looks a little bit different, where you get kind of the Hitchin component for split G2. And so, I mean, these are the only kind of rank 2 simple groups. So the other ones, you can write things down, but it's not kind of naturally a component anywhere.
So you haven't actually described it. It looks like there's been this jump where you were talking about cubic differentials, and now you're talking about Hitchin systems.
Yeah.
You haven't told us.
I haven't kind of explained exactly how to get back. Yeah. Well, I mean, the Hitchin systems, I mean, the cubic differential lives here. And so kind of there's this theory that says that if you do this, then you can parameterize all the components of the representation variety. And it's kind of a fairly recent theorem of Labrie that kind of this sort of thing works with all of the other rank 2 cases as well. So with spin 4 and split G2. Or SP4, yeah.
Can you say again what H is?
So H is a conformal metric. So let me write down, yes, let me say what H is. So this is actually, so that was going to be the next thing. I think I'm going to have to write it over there. So let's say what H is. And so this is actually kind of part of the reason that this is such a tractable problem, is that in this situation, the Hitchin system reduces to a single equation. Reduces to an equation for H. And so H is going to be equal to e to the mu times sigma. So sigma is a background metric. And then, so the Hitchin system reduces itself to kind of a single semilinear equation. And so having kind of a single semilinear equation, you have a lot more techniques. So the maximum principle works well. I mean, these signs are the right way for the maximum principle to work. So you get, so in particular for each cubic differential, you get from standard techniques that the existence and uniqueness of a solution to this H. And then once you have this H, you can kind of, that's kind of, you get the entire structure.
So, I mean, I'm intentionally asking dumb questions. I'm just trying to connect this with things I know. So, for the PSL2R case, it's really quadratic differential, right?
Yeah, with PSL2R case, it's quadratic differentials, and it's related geometrically to harmonic maps between hyperbolic surfaces.
Or even, yeah, so the Dyer-Spencer theory would say the cotangent space of the of type move space is the space of quadratic differentials.
Yeah,
so
exactly.
This gives a way of giving a geometric interpretation.
Yeah, yeah. And so this H, I mean, if you look into, so there are various ways, which haven't really planned on kind of going into the details. So there is a natural surface in R3 called a hyperbolic affine sphere. And so this H is something called the Blaschke metric. So this hyperbolic affine sphere, so this is, it has a kind of a center. It looks like a hyperboloid. It has a center at the origin. And then you look for invariant properties that are invariant under SL3R actions. So this H is kind of related to the Euclidean second fundamental form, but it's invariant under this larger group. There's another thing that you can do that's, so there's something called if you do this setup in this kind of rank 2 case, so not just this case, but kind of also kind of higher differentials and larger matrices, then there's something called TOTA system from integrable systems. And so this is kind of the solution to the A22 TOTA system. So I think I'm kind of doing this. I think it's like this. So A2 is going to be this is going to be the Dynkin diagram for SL3. And then typically that will give you a pair, since it's rank 2, that will give you a pair of 2 equations. But since A2 has a symmetry, which you kind of denote by this, you get a single equation in this case. So.
In the rank 2 case, what you made the limit is constant scalar curvature. Is this the same as prescribing the scalar curvature of A to be norm square of U, or is
Yeah, it's something like that. Yeah. You prescribe the scalar curvature. Yeah, exactly. Thanks. Well, I mean, to be norm squared of U, but then there's also this term, right? It's like plus something, right? Yep. Any other questions? Okay. All right. So let me mention kind of, there's a geometric structure. And so again, I'm going to be talking about on sigma, and this is kind of really special to this case. So this kind of construction of sigma u, this gives, so the nabla that we construct by Hitchin's theory will give what's known as an RP2 structure on sigma. And so what this is that, in other words, there's going to be kind of coordinate charts on sigma in RP2, and the transition maps are constant matrices in PSL3R.
So this is a flat projective structure.
It's a flat real projective structure, exactly. Yep. Okay. And so let me kind of go, so this is the geometric structure. So this is kind of the Thurston style or Thurston-Ehresmann style XG structure. And so let me go over kind of, there's a nice argument of Goldman that was kind of carried out in this case by Baraglia, how you can kind of get this from okay. So in this case, what we're going to have is so let little s be a a section of the trivial line bundle which is inside of E. Okay. So there's going to be a section, trivial line bundle. You can just take kind of the standard trivial section, okay, with the standard parameterization. And then let P, so let kind of X naught be a base point. So let's just kind of go to the universal cover here just to be a little bit nicer. And let P be a path from X naught to some Y. Okay? And so, of course, the connection is flat, and I've kind of gone to the universal cover, so the parallel transport is going to be independent of the path. Good? And so let kind of, I guess, 2 sub P be the parallel transport. Along path by nabla. Okay? So, in particular, what you have is, so I'm going to look at kind of, there's going to be a real part here, which I haven't described the real structure, but I want to kind of look at the real structure anyway. So X naught going to E real part P of 1. So P of 1 is equal to Y. Okay. And so what we're going to do is we're going to consider the following construction. So this is due to Goldman. Good? So if you consider this parallel transport, so you look at kind of this, this standard section, standard with respect to this holomorphic structure. You look at kind of where the standard section lands at the end of your path. You're going to use parallel transport to pull it back to this common vector space, ER, which is like, so this is like a copy of R3. It's going to be pulled back to a non-zero vector, and then you can kind of project it down to RP2. Okay? And so it turns out that this construction, this gives the RP2 structure. And I guess one of the, I'm not going to go through. It's a local diffeomorphism. Yeah. Yeah, it's going to be a developing map, a local diffeomorphism. And you have to use the fact that, I mean, this, you can, this extra stuff here, when you look at the real part of this, you can kind of do a little bit of algebra. So the real part of essentially this plus this has to be related to the tangent bundle, right? And so essentially this real part of E, the part that's orthogonal to 1, is going to be the tangent bundle. And so that's how you can kind of integrate out this structure.
So, I mean, so the geodesics for this projective structure would correspond to the inverse image of a two-dimensional linear subspace. What does that geometrically mean in terms of these? I guess it's just a different structure on the surface.
I mean, the geodesics are going to be kind of the projections of the parallel transport.
So in particular, if you were to, I guess kind of the more classical version would be if you were to take a flat projective structure that came from the hyperbolic metric. What would be the corresponding Higgs pair?
Okay, yes, I should have mentioned this earlier. So if you have kind of a flat hyperbolic metric, then that just corresponds to the case U is equal to 0. Okay. So if you have kind of the case of kind of a hyperbolic metric, and so of course, so if you look at the Klein model.
So have you somehow fixed the hyperbolic metric on the given Riemann surface in the construction? I don't see where it is.
Well, I mean, there's a background metric here. which is typically you choose to be hyperbolic. Yeah. So the hyperbolic metric, so in the Klein model of hyperbolic space, this does give you, so a hyperbolic metric does give you a real projective structure. Because you remember the Klein model has the geodesics are straight lines in the disk. And so the isometries do like, what is it, P SO21 lives in PSL3R or something like that. So these are, so this gives the case U is equal to 0 and kind of a RP2 structure.
You might just draw that for people who are not familiar with
Yeah.
Klein model of hyperbolic space where the geodesics become straight lines.
Yeah, so the Klein model of hyperbolic space, so this is a non-conformal way of writing kind of the metric on hyperbolic space. And so so you kind of draw a disk model, but the geodesics are straight lines. And so this is a Riemannian metric on the disk, whose formula I can't remember, but it's not conformal with respect to if you put this inside of the complex plane, it's not naturally conformal. So, yeah, thanks. Okay. All right. Okay, so let me just kind of mention again a little bit about what's going on here. So for our construction, this kind of this M, this harmonic map. So this can be kind of so in this case, it's you can think of it into this symmetric space. So the symmetric space for this smaller group, SL3R. So this is, it actually is minimal in our case. So since you can write kind of the Hopf differential is the trace of phi squared, which turns out to be 0 in this case. And it's also kind of the equivariant, of course, under the holonomy action. Good? Okay. So let me kind of write down the theorem. So I've kind of done, I hope, enough background to give people an idea. So with Tamburelli and Wolff, so let capital S be the symmetric space. So as t goes to infinity, so for tu here, we're going to have a limit of m infinity into what's known as the asymptotic cone, which I'm going to write something wrong here. I'll try to explain how wrong it is. So with this, naturally when you kind of do this, the various objects here will scale. So, so we're going to take a limit of this kind of symmetric space S with respect to this rescaled metric. And that's because kind of the various quantities such as m and h and other things are going to scale at a t to the 1/3 power. Okay? So this limit is not a standard limit. So in order to kind of get this to be a nice space, you need something called a non-principal ultrafilter, which is like a souped up version of subsequences. So basically, so let me just say kind of one thing. And we were kind of horrified. We thought that we would be able to not have to use this, and we don't use it in great detail. But so this non-principal ultrafilter, so you know that you have to take subsequences. You know that kind of by the diagonalization argument, if you need to take kind of a countable number of nested subsequences, then you can do so, right? There are some kind of geometric constructions where you may need to kind of, in effect, take more than countable number of subsequences. And so this thing called a non-principal ultrafilter will allow you to take limits here. So the non-principal so I can say a little bit. I mean, it's a finitely additive probability measure on the natural numbers. So you have to kind of take a sequence to infinity, call that the natural numbers, such that every set has measures 0 or 1. So the measure 1 ones, those are going to be like the good subsequences, and the measure 0 are the bad ones. Also such that all finite sets have measure 0. So these things need the axiom of choice to construct them. And so in particular, so this is like, this depends on something worse than a subsequence. So that's kind of so that's just kind of a feature of the theory here. So apparently, if you do this with kind of rank 1 symmetric space, you can get by with subsequences, but with rank 2 and higher, you need this construction.
So is the limit non-unique? Depends on a choice?
I think what happens, I mean, I think it's worse than that. I mean, so if you assume the continuum hypothesis and you're doing this to a symmetric space of non-compact type, then the limit is unique. But I'm not sure if kind of if there are kind of canonical isomorphisms between them. So these spaces are kind of very messy. So, okay. Okay, so now what we're going to do is we're going to have so this I'm going to call kind of ST. So so just with this rescale, and we're going to kind of limit to m infinity. Okay? And so then kind of the theorem is that kind of the image of m infinity is going to be isometric to the universal cover with kind of the pullback of this singular flat metric, u to the 2/3, with, so isometric with kind of the induced, kind of think about this as a path metric, but it's not a totally geodesic embedding. Okay? So let me say a little bit about kind of the...
And you say this conclusion depends on whether the continuum hypothesis is true, or is this...
No. The conclusion is fine. The conclusion is fine. It's just kind of... this space is like really, really big. So I mean, I'm going to... so let me just kind of say a little bit about this space, S infinity. And I don't have kind of a full grasp of this thing. So this is going to be a metric space, of course. So it's a complete non-positive curvature metric space. Okay? It's going to have rank 2. And so in particular, through every point and kind of contained in every geodesic, there's going to be an isometric copy of R2. So these kind of copies of R2 are called apartments. And this thing is called a real building. So in some sense, this real building is kind of a generalization of a Tietz building. So when Tietz kind of first described a building, I mean, he had kind of, there's a situation where you have kind of various things like this, but there's kind of discrete branching in terms of how these R2s fit together. So in this case, there's going to be a continuum of branching at every point. So it's kind of a much messier space. And so the real corresponds to this continuum. Okay. So the question is which R2? So this is, so if T is kind of the maximal torus, then of SL3 in the Lie algebra, it's going to be the T star. So this is where kind of the Weyl chambers live, right? So this is the structure on R2, and so this is going to be the, so you can think about this. So this R2, we can kind of think about 3 eigenvalues in the Lie algebra, lambda 1 plus lambda 2 plus lambda 3 is equal to 0. And we're going to look at the positive Weyl chamber okay? Okay. So what happens with this thing is that with this real building, what you do is you can kind of glue together the copies of R2 which respect this kind of Weyl chamber structure. Except it's kind of we can think about this in terms of the affine Weyl group. So it's not just kind of reflections across these lines, but also kind of any translation. So basically, kind of these apartments, so they may be glued together along, say, diamonds. So a diamond may be something like this. So if you take kind of this a Weyl chamber, then you kind of move it up by the affine group, you do something like this. Okay? And so these lines are going to be parallel to the various walls in the Weyl chamber. And moreover, there's going to be, at each point, so at each, there's going to be a continuum of apartments at R2s kind of along each wall in the Weyl chamber. So it's a very large, messy space. And that's that. So I should say, so I guess I don't have much time left. So let me go to, there's a picture that I wanted to display. Picture, okay, good. So let me show you how this works. So this is a triangle group. So this is going to be the 3, 4, 4 triangle group. So you can see basically that there are kind of 2 different sorts of intersections here. So there's going to be one with, oh, I guess I don't have the, is there a, there's a pointer, okay, yeah. All right. That, I don't know.
Oh, but it's not a laser pointer effect. That's something that's actually.
Okay, yeah. No, okay, so maybe I'm not going to be able to do that. So anyway, there are kind of 2 different points, sorts of points here. So there are ones with kind of like the 3 point. Okay, that one, okay. Oh, there it is. I just have to keep it down. So this is going to be a 3 point, whereas these 2 will be 4 points. So you can see that kind of with a 3 point, there are 6 triangles come together. With the 4 points, there are 4 triangles come together. Okay? And so what happens with these triangle groups is if you have a triangle group where all of these 3 numbers are bigger than or equal to 3, and in order for it to be hyperbolic, we want it to be at least one of them strictly bigger than 3, then you can encode a cubic differential on this orbifold. So you think about the kind of the triangle group, you look at kind of the, typically the triangle group, you think about it in terms of hyperbolic reflections across the edges of the triangle. So you look at kind of an oriented orbifold double cover, so you can do some kind of complex analysis. So it turns out that on this kind of orbifold quotient, there is a unique cubic differential up to scaling. And so when you kind of take this cubic differential up to scaling, and you do this procedure with it, this metric turns all of these triangles into Euclidean equilateral triangles. So if you look at this point is actually going to be a smooth point. The neighborhood of this point is going to lie in an apartment in the asymptotic cone. And so and that's because there are just going to be 6 equilateral triangles coming together at this point. Whereas if you look at this point over here, you're going to have 6 equilateral Euclidean triangles coming together. And so that means there's not going to be a single apartment that contains a neighborhood of this point. So there's going to have to be, I think kind of the procedure is you can kind of put maybe 4 of these triangles together to remain in a single apartment, then no more. So you can see that you have to kind of pass into another apartment as you kind of go around this point like this.
Are the vertices just the zeros of the different?
Yeah, so the vertices, this is going to be a 0 of order 1. So these kind of 4 points, those are both going to be zeros of order 1 for the cubic differential. This turns out to be not a 0 of the cubic differential. And yeah, so these vertices, that's going to be the zeros, and that's going to be, so you can see kind of that in general around kind of the zeros of the cubic differential, you're going to have this sort of branching behavior. Where you kind of jump out from one apartment into the next. Okay? All right. So I don't know, how much time is there? Like not much? About 5 minutes. So I'll say kind of a tiny bit. So I mean, I don't know, but I think this is kind of quite a nice geometric picture. So I'm going to go back to the blackboard. So let me just say a little bit about how to prove this. So kind of the idea is we're going to analyze the parallel transport. So what we're going to do is, so we're going to pick a base point. And so let's just do this in the universal cover. And then we're going to take kind of a geodesic path. So via geodesic paths, you can kind of get to any other point. So geodesic path with respect to this flat metric. So we're going to have kind of, so this is going to bounce a bit according to the zeros. Okay, and so now what we're going to do is we have kind of these various estimates here. So so we have kind of these eigenvalues of the holonomy. So these are going to be kind of determined by the cubic differential. So away from the zeros. Okay? And so if you write this down, if kind of u is dz cubed away from the zeros, z is r e to the I theta, then so these are going to be so if you have a path of length L, Euclidean length L, so then you're going to just kind of, essentially you're going to take kind of the horizontal coordinates of the path vector multiplied by the third roots of unity. Okay? And so then you're going to order these so that this vector lies in the positive Weyl chamber. Okay? Or the closure of the positive Weyl chamber. And so this is kind of a picture due to Anne Perot. And so then kind of the metric space distance is just going to be So this is going to be, let's call this DI. Okay. Let's call this DI. So basically what you do is you compute, there's a distance from each of these. The distance will kind of add in this way, but it's essentially going to be a vector value distance, which originally was introduced by Perot. And so kind of the idea with doing this is that, so let me just kind of say this a bit quickly, is you have to kind of find kind of, you can approximately diagonalize, so this is going to be a parallel transport map. And so these are going to be, if you write this in terms of kind of a nice enough frame, so this is along a path, this is a linear system of ODEs, 3 by 3 matrices. So, and if you write it in a nice enough way, it's going to be kind of approximate, with some rescaling, it's going to be kind of approximately a constant plus some error terms. So the kind of the ODE theory will give you that you're going to have kind of approximately some eigenvalues, some kind of solution plus the error terms. But kind of the problem is that the error terms are rather large. So, so what we, and then kind of again here, we're going to have kind of other things to do. We can't actually go through the 0, so we use kind of some other estimates here. So it's all about kind of controlling the error terms, which are not very big, so which tend to be quite big. So in particular, kind of the holonomy around the CI is essentially going to be the exponential map t to the 1/3 lambda I, lambda 1I, t to the 1/3 lambda 2I, t to the 1/3 lambda 3I, okay? Plus the error terms. But then the error terms, so you notice that the largest one exponentially grows. This one exponentially decays. So the error terms in general are going to be enough to swamp these two. So the only thing you can get is the largest eigenvalue. So it turns out, and you can do something else, kind of some other analysis to make sure that these things fit together near the zeros. But kind of the idea is if you go along these paths, the only thing that you can get without errors is the largest eigenvalue. But then you use kind of some magic of SL3 in that if you take the same path in reverse, you can get the smallest eigenvalue. And then in SL3, there are 3 eigenvalues. In the Lie algebra, they add to 0. So you can get the middle one as well. So it's kind of, so the analysis is a little bit, so based on kind of the fact that you can kind of find the largest eigenvalue, you end up getting all the eigenvalues you need and kind of this, so it kind of heavily depends on SL3 in this, at the end. Okay, thanks.